Alrighty, 2018 question number 4. We're given a table, and this table talks about the height of a tree at any time t is given by the twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. So this is a classic table problem, right? So part A, like many table questions, asks us to estimate h prime of 6. So the derivative of h, the instantaneous rate of change of h at t equals 6. Well, t equals 6 would totally fall right here between 5 and 7. So my best approximation of h prime of 6 would be using the average rate of change between 5 and 7. So to estimate h prime of 6, we're going to look at h of 7 minus h of 5 divided by 7 minus 5. That's our average rate of change formula, our secant line slope. So we know that's how we approximate derivatives. And since 6 fell between 5 and 7, that's why we're using 5 and 7. Alrighty, so let's plug in some values here. Let's say h of 7, you're 11, and h of 5, you are 6. 11 minus 6, and 7 minus 5. So it looks like h prime of 6 is approximately, h prime of 6 is approximately 5 halves. And it says, using correct units, interpret the meaning of h prime of 6 in the context of the problem. So I've already said that h prime of 6 is 5 halves. But what does that mean? Well, since it's the rate of change, in the numerator I have meters, and then the denominator I have the time, years, so it's meters over years. So meters per year. So that would tell us how fast the tree is growing in meters per year at exactly 6 years. So let's write this out so it makes sense. At 6 years, because that's the time we were looking at. At 6 years, the tree is growing at a rate of 5 halves meters per year. Cool, so that answer should have all the parts that I need. It says when, and it says how much, and it even uses the correct units and relates it back to the problem by talking about the tree growing. Alrighty, time for part B. Explain why there must be at least one time on that interval 2 to 10 such that h prime of t equals 2. So we're looking for this to guarantee an h prime of t that equals 2. So when we talk about guaranteeing something like that, explain why there must be. We're either thinking IVT or MVT. Now in this particular case, since I'm comparing h prime to h, you see that those two are on different levels. I have function h and its derivative h prime that I'm comparing. So when we're on two different levels like that, we know that's going to be MVT. So am I able to use MVT if h is differentiable and continuous? Yeah, and h is differentiable and therefore continuous. So I can use MVT. So let's refresh our memories on what MVT looks like. MVT looks like, hey, the instantaneous rate of change is going to equal the average rate of change. Cool. So the first time I did this problem, I was like, I just looked at 2 to 10, like the problem tells me. So I ran through it and I was like, okay, h prime of t equals h of 10, so 15, minus h of 2, 1.5, over 10 minus 2. So I had 13.5 over 8, and I don't know what that is, but it's definitely not going to be 2. So the first time I looked at this problem, I was like, uh-oh, that's not going to work. So I had to think about it. Is there any interval in there where we will have an average rate of change that's equal to 2? So the whole big papa 2 to 10 interval doesn't work for us. But maybe somewhere in between 2 and 10, there's an average rate of change. Because I got all this information up here. Maybe somewhere in there, there's an average rate of change that's equal to 2. So that didn't work out. Let's see what else we have. Let's check out from 2 to 3. From 2 to 3, I could do the average rate of change would be h of 2 minus h of 3 minus h of 2 over 3 minus 2, which would be, what's that going to be? A 0.5 over 1, which again is not going to help me. So let's try another interval. Let's try 3 to 5. So I can do h of 5, which is 6, minus h of 3, which is 2, over 5 minus 3, which is 4 over 2, which is 2. So this is my interval that would guarantee an h prime of 2. So the whole big papa interval didn't work, but if I break it up into small intervals, I can find one, and I did find one. It was from 3 to 5. So my work isn't going to be this. It's going to say, hey, h prime of t equals h of 5 minus h of 3 over 5 minus 3. And that's, what did we say that was? 6 minus 2 over 5 minus 3, which was 4 over 2 equals 2. So h prime does equal 2. We're guaranteed that h prime will equal 2 on that interval. So we need to write out our work. Whoa. So I need to write this out in a nice way that would satisfy the people that grade my work. So first of all, I showed my math. That's good. But now I got to show why I was able to do that math. So I would start with saying, hey, because h of t is differentiable, which implies that it's continuous, on our interval of 2 to 10, but we even broke it down even smaller than that. We even broke it down to 3 to 5, which is okay. We just, because that's within 2 to 10. So because ht is differentiable and therefore continuous on the interval 3 to 5, MVT guarantees a place. I'm just going to call it a C because that's how we used it whenever we learned about MVT. It guarantees a C on the interval, and our interval, we broke it down to be 3 to 5. Where h prime of c is equal to 2. And we showed all of our work there, and everything looks pretty darn good.